Alright, man. We gotta go back to the land of arcs and sparks. My phone makes it look brighter than it is, man, but it's kind of scary in here. Hang on. Family's gonna think I'm nuts. Let's get some light on the subject here. I got a few things I want to mention that I neglected to the other day. Hang on. And so I'm basically ready and set up. I've got the hidden cheat sheet that will remain where it is. I did a bit of cleaning in the land of arcs and sparks, otherwise known as my bedroom, and I hope I didn't make anyone nervous, for I'll never truly clean my bedroom. Hang on. Okay, so there's perfect. So there's 4 or 5 things I'd like to touch on, and they're all electronics related. And if you want to bail, see the comments see the video description regarding bailing at this point. And so I'm going to zoom you in. Hang on. I want to talk about voltage burden first. I don't know if you've ever heard the term, but the term, it is a voltage level, the voltage dropped on a shunt resistor or a current sensing resistor. Okay? And you know Ohm's law's the Ohm's law formula, E equals IR. We calculated in this hypothetical example that RX value is 0.05 ohms. And if we're flowing 20 amps through it, that wire will drop 1 volt. Knowing this, you can calculate how much power that wire dissipates. It's more than you might think. It gets warm to the touch, which is why I like to use wire, because it dissipates the heat, and it only gets warm, not hot. And so you don't want that wire getting really, really warm, because the resistance changes and your accuracy of your amp meter will change, will get worse. The more stable that resistor is in value, the better. Anyway, so in this case, our voltage burden on that shunt resistor is 1 volt. Therefore, on a power supply, you really don't want that current sensing resistor on the output side of the regulator, although that's the most accurate place for it. But boy, if you do, if that thing is set up to output 13.8 volts and under a 20 amp load, if that voltage sensing resistor drops 1 volt, now then your output's going to drop from 13.8 to 12.8 volts. If you can live with that, great. Do it. Can I live with that? Oh, heck yeah. Heck yeah. Believe me, the rig's perfectly happy with 12.8 volts. Voltage regulation for me is not a huge issue. For me, the main thing is that it's a linear power supply with 0 hash. Another way of getting around that voltage burden loss is to put this current sensing resistor on the input side of your regulator transistors, and that way the regulator will take that into account and compensate. But you're going to always have the loss of the regulators introduced as error in your amp meter if you do that. But again, it's doable and it works. So that is voltage burden. The voltage drop on a current sensing resistor or shunt resistor on an amp meter. Or for that matter, and this is important, guys, your DMM. you plug your test leads into the 20 amp jack on that thing and go to measure the current of an appliance or something that flows a significant amount of current. What do you think the voltage burden of your meter is when set to current mode? Because doesn't only include the shunt resistor in your meter, which if you take it apart and look is a little metal bar. It looks like a coat hanger. And oftentimes it'll have a compression in it or a nick. And that compression or nick is used for calibration. The more they nick it, the higher the resistance goes. And so, but you have to include the resistance of your god-awful Chinese test leads now in your voltage burden, and it can be significant. You want to see, slap another DMM, set the voltage mode across it. You know what I'm saying. Anyway, moving on, man. I'm babbling now, so let's move on. Okay, I want to point something out. Pause you. Okay, on the expanded scale voltmeter that reads 10 to 15 volts, I felt I was kind of confusing and unclear about a couple things. When I talked earlier about you can put a pot here and connect this to a known voltage source and adjust the pot until this reads full scale, I was wrong in that first video. I said you'd hook this to a 15 volt source. That's not true. You hook this to a 5 volt source, adjust the pot for full scale. Okay? When you do that, you've got a voltmeter that reads 0 to 5 volts. It's just simply that, right? And hang on, man, I gotta scratch my foot. I'm dying. I've got fleas. I'm joking about that. I'm very allergic to fleas. Okay, and so what you've got then is a voltmeter that reads 0 to 5 volts, okay? You're dropping 10 here, and basically, dropping 10 here, and adjusting this calibration pot so that if you input 15 volts here, you drop 10 here, you adjust this so you read 5 here, and this reads full scale at 15 volts. It'll just start moving at 10 to 15 volts, okay? 10 volts is your 0 point, 15 volts, which is dropped to 5 volts, is your full scale point. I hope that's clear, man. It's the best I can do. I'll probably think of another way to word it better as soon as I hit the stop button. Also, I talked about this pot here. I say it's 10K. Well, you could eliminate this resistor by choosing a much lower value of pot. That's fine. Like I mentioned that the current flowing through this Zener, when you've got 15 volts applied, is about 25 milliamps. I think that's what I calculated. We'll just use a 1K pot in place of this resistor, and you'll drop your current in half, but that's fine. If you go from 470 ohms to 1,000 ohms, so you got 12 milliamps of current flowing, that's fine. That diode's happy, and with that low a value of pot, you will not load it at all with this voltmeter. And it's dead nuts accurate, man. So let me see. Yeah, okay, we got that one. Okay, I'm going to pause you. Okay. I believe I was wrong in the first video. You can see what I've crossed out, because I was wrong about something I said. And that is, as this voltage starts out at nothing and starts approaching 15 volts, nothing happens here. No current flows until you hit the value of that Zener, okay? Let's say we set that at 15 volts. That's a 15 volt Zener. Let's say we're going to start at 0 and go up to 20 volts on the input, okay? Start at 0, we're going to go up to 20. This is a 15 volt Zener. As we're starting at 0 and going up and up and up in voltage here, there's no current flowing through this resistor and Zener at all. This zener is a very high impedance or very high resistance in this case, since it's DC. It's a very high resistance, exceedingly high. And if this is anything in your junk box, no current will flow until you hit the zener voltage. And once you do, and so since this is an exceedingly high resistance and this is in comparison very low, this point is in effect tied to ground. But once you hit that zener voltage and current starts flowing, as soon as the voltage at this point starts climbing and it triggers this SCR, it's not a triac when it's mounted on the output of your power supply. It's an SCR meant for DC duty, and it triggers and it shorts the shit out of the output of your power supply and blows the thing. It'll blow a fuse or blow whatever. It's better than blowing your ICOM or your Kenwood TS890. Wait, those have a built-in power supply, don't they, you Fred? Anyway, man. Now, speaking of, I started looking at that NuMar power supply, and we're going to take a look at that right now. I'll show you something that really surprised me, what they did with this crowbar. This is what you call a crowbar overcurrent protection scheme, like dropping a crowbar across the output terminals. That's what you're doing, dead shorting them when that fires. Well, they did it a different way in that NuMar, and I'm looking at it right now. I gotta make this short, man. I'm gonna pick my phone up and hang on. Oh man, I'm really sorry. You didn't deserve that shit. Hang on. Okay, I got looking at this original regulator control board in this NuMar supply, and the first thing that popped out was the big SCR. But in this, I got looking at it. In this case, it's not an SCR; it's a triac. And I thought, what the hell? And then I noticed, why the tiny little wire on that thing? That's not going to blow anything. That's no fail-safe. It'll just roast that wire in half once that thing triggers. And then I start looking at it and tracing the wires back, And you know what they're doing? They come back to the fuse socket and the fuse connector, and what they're doing and that's a triac, when that triac triggers, they're shorting it right at the fuse, right at the AC input. On one hand, it's going to draw a lot less current in the triac circuit because it's at 120 volts. It's only got to flow a few amps to blow the main fuse. When it's mounted, when you're using an SCR mounted on the output in true crowbar fashion, that thing's got to flow tens and tens and tens of amps. The instantaneous current flow will be hundreds of amps, but the supply quickly blows. Let me try to refocus. I reject their scheme because if something, and when we say something goes wrong and it overvolts, we're talking about a shorted pass transistor. When that happens, you'll apply your full capacitor voltage to the output terminals. And that capacitor voltage, they're probably running, anywhere from probably 18 to 20 volts, 22 volts, probably not that high, but 18 to 20. Anyway, the key is that cap voltage is shorted right to the output terminals with no current limiting. Those two caps in parallel, what do you think they'll do to your ICOM or your Kenwood or your Yaesu if you dump their full output into it? In my opinion, it's far better and safer to crowbar the output right at the output terminals. Mount the SCR on the output terminals. And surely when that device triggers and those output terminals short, your rig voltage goes to 0, and right now, whilst chaos happens in the power supply, you let your fuse take care of the chaos. I hope that makes sense. I was going to ask you guys' opinion. Should I just rebuild this board? But let me show you why I chose not to. Because, where is it, man? There we go. That chip is an LM723 voltage regulator. And I'd rather go with a more modern design, you know. And the designs are everywhere. I'll just find one I like in a publication and go with it. And so that's my little 5-minute addendum, my my little errata video that's now 16 minutes and 4 seconds long. So with that, from our good friend Al and this poor, terrified woman, I wish you 73 and be well, man. Take care.